Okay, let's now continue with the second part of the video lesson. So we are done with the two recursive programs, and then we'll now come up with something which is almost identical to the program number 2. Again, I'll be doing the same thing. But little differently. It may look like as if I'm trying to confuse you, but the idea is not to get confused in the future. I'm trying to confuse you a little bit, so the whole idea is to make matter absolutely clear as of now. So I'll be using another method, or perhaps I could write second method to print the string backward. So let's come up with the program itself. So as usual, I'll have the function definition, the name of which will be BP, and then you will have the same string argument of S and the length of string to be stored in the variable of N. Alright? So again, we'll have the if the value of N is greater than 0, I'll use a variable called K. And then K is equal to length of SG minus N. Just hold on, just complete the program and then I'll come up with the explanation. So now this time, instead of printing the characters first, we'll make the recursive call. So this time it will be BP, and then you will have SG, and then again you will have N minus 1. After this, we'll print SG of K. Okay, so these are the statements of this if statement, and then if the value of N is equal to 0, I'll just have the return statement with no value. Okay, it returns something, but that something is nothing. It doesn't make much of sense, but sometimes these are very useful statements in order to redirect the control. And then, so this is nothing but the function definition, and then you will have the function call as S is equal to, this time I'll just keep the number of characters to 3 in order to minimize the number of frames up on the stack. S is equal to, I'll just have TIB, only 3 characters, and then the function call will be BP, okay, BP, and then you will have S, length of S. Okay, so this time I'll not have the minus 1 because the program is a little different, even though both programs they do the same thing. So this will be the function call. Alright, so let's move on with the stack. So this will be the frame for the main part of the program. Okay, so this will be the main part. So in this, you will have the value of S as TIB, and then the function call of BP, you will have tip, alright, and then the value of length of S will be 3. Okay, so these two statements will be staying in the frame which belongs to the main part. And then after this, so again as usual, this is nothing but the function call, as a result of which you will have another frame. Okay, so this frame will be represented by, from here the control jumps to this, so this time it will be BP, you will have the tip, and then you will have the value as 3. Since I'm passing the length of S directly to the N, there won't be any change contrary to the earlier program. Okay, so once I get in, this condition will be true, the condition will be true, and the value of n being 3, the condition will become true, and the value of k will be the length of SG. The length of SG will always remain as 3. Alright? So 3 minus 3. The value of n is again 3. So 3 minus 3, the value of k will be 0. Alright? So the value of k as 0 will be retained in this frame of the stack. Same is the case with value of n being 3. And then you have yet another call. You have yet another call as BP. The value of SG will always be TIB. And then this time there will be a change in the value of n. So the value of n will now change from 3 to 2. But you need to take note of a special case here. This statement will not be executed because you have the function call. Unless and until the complete function of this call is executed, it will never ever move on to the next statement. Okay, so since we now have the function call, another frame will be created. So this time, okay, I just mean to look like, to make these look like frame, and then you will have another call. This will be BP, and then TIB, and then you will have again 2. Alright? So the value of n will be 2 this time, and the value of k will be again the function itself will be called again. This particular condition will be true since the value of n is 2, and the k. The length of SG will always be constant, which will be 3, and the value of n has been just changed from 3 to 2. Remember, thanks to the statement of n minus 1. So this time the value of k will be 3 minus 2, it will be 1. The value of k will be 1, and then you have the function call again. So this time the function call will look something like this. It will still be tip, and the value of n, the value of n will now be 1. Okay, look at this. SG, the value of SG is tip. The value of n should be deducted by 1 again, so it will be 1. And then again, when the computer sees this function call, another frame will be created. I guess this will be the final one. Okay, so this will be the final frame, and the function definition or the header. So this is what we actually refer to as the function header. The function header will still be BP, TIB, and then you will have the value as 1. So this time in this particular frame we'll have the value of n as 1. However, the value of k will change to again, this will be 3 and this will be 1. So 3 minus 1 is 2. I hope you're clear with this. The value of n being 1, and the value of length of SG will always be 3. So 3 minus 1, you'll have the value of k as 2. Again, BP, you have yet another function called TIB, and this time the value of n will now be 0. The value of n will be 0. Alright? Okay? So again, finally, you will have one last function call to BP, and this time the value of n is 0. Alright? So we'll come up with the final frame of the stack. So the function header will be BP, and you will have tip. So this time the value of n will be 0. Since the value of n is equal to 0, the condition becomes false. The condition becomes false, so these two statements will not get executed. Rather, this particular statement will be executed. Alright? So you have the return statement. You have the return statement, right? So what happens here is you have the return statement, right? Okay, right, the value of k. Okay, right, you have the return statement which returns nothing as such. So what happens here is, from this particular frame, this particular frame, since it's returning a value, even though you don't have any value as such, but nevertheless, it seems to be returning something. Okay, so it's returning something, but there is no value as such which is being returned to the topmost frame of the stack. So what happens here is, the control will return back to this particular frame. Okay, so this will now replace the function call of BP tip of 0. So this value, it's a little weird for me, but a value is being returned, and this value will replace the function call, and then this will be off the stack. Or to be technically, if I say it, this particular frame will be popped off the stack. And then what happens here is, once I am done with this, I'm now finalized with this function call. This function call is taken care of, right? Even though no value as such is replacing this, but at least I am completely done with the execution of this function call. But when I'm done with this function call, am I done with the execution of the complete frame as a whole? The answer is no, because right under each function call you have one statement remaining. For each of the function call, there is one final statement which remains to be executed, which is nothing but print SG of k. So once I'm done with this particular function call, you have this pending statement, which will print the value of print and then SG of k. The value of k being 2. The value of k is 2. And this particular frame, the value of k is stored as 2. And then you will have SG of 2. SG of 2 will help us to print which character. The character has to be, this is 0, this is 1, and this is 2. So once I am done with this function call, it's not the end of the function definition. Alright, you have one more pending statement which will print SG of 2, which will give us the answer of B. Am I right? 0, 1, 2. Alright, so with this, I am done. I'm done with the complete the function definition. So again, I need to go back. Okay, I need to again go back because the program is not yet over. You have one pending statement of printing. You have one pending printing statement of each of these function calls. So once I'm done with this tag will get off the stack. This frame will get off the stack. So again, it goes back, right? It goes back, and then once I'm done with this, what happens is you will have the look at this. This function call takes us to this. Okay. So I am completely done with the execution of this function definition, which means I am now done with this particular statement. Okay, so again you have the pending statement of print SGK. So you will have print SG, the value of k is 1. So this will print the next character of SG of 1. SG of 1 is I. You will now have I, and then again this particular function definition has been called by this function call. Can I now say the function call of this? Okay, function call of BPT2 has been executed completely. I'm done with the function call. I'm also done with the printing statement which is pending. And then again, since I'm done with this, I'm done with this. You will now have the printing statement of print, and then you have SG of k. The value of k is 0. Alright, the value of k is 0, and then you will get the answer as T. So this is, how I print, the string backward. From here on, what happens is, since this frame as a whole is called by this function call, I can now say that I am completely done with this particular task. May I know the statement number of this? The statement number of this particular statement is the last statement number of the program. So with this, I come to the complete halt or complete end of the execution of the program. Alright? So it may look a little messy, especially I'm not too good at drawing, but if you pay proper attention, you should have no reason to get confused. Alright? So this is how the computer visualize the actual operation when it comes to the invocation of recursive calls. So let's go to the next program. The next program will be something very similar. Okay. So if you have understood very well to this point, you should be able to handle, the next question. This time it will be a calculation of x raised to n. I've shortened the question considerably, in order to save the duration of the video. So if I take an example, let's say the value of x is 2 and the value of n is 3. 2 raised to 3 is 2 times 2 times 2. This will give us the answer of 8. Alright? 2 times 2 is 4, 4 times 2 is 8. So regardless of whatever value you have as for x, for n, the program should be able to handle with absolute ease. So again, you have a situation of recursive call. This time I'll just write the program. This is for your understanding's sake. At any cost, you should be able to understand how the actual operation, is processed by the computer. Only then you will feel at, comfort writing programs for such questions. So what we'll do is, for a change, we'll just write the program, and then, if need be, try to come up with these free, as well as the stack, in order to understand better. So let's write the program. Okay, so it's going to be like, alright, write the program here. Okay, no problem. So again, let's say the function definition will be, the name of the function will be power, and then we'll have 2 arguments. The first will be b, which will store the value of base. As per this particular example, the value of b will be 2, and the value of e will be 3, base and exponent. So this is the function definition. Now the question is, how will this recursive program must come to an end? For this particular example, if the value of e is 0, if the value of exponent is 0, you have a base case here. Like I said again, a case where I would actually draw the recursive program to an end. I'm sure you must have learned this when you were in junior classes. Anything raised to power of 0 is 1. So this is one way by which I could come up with a base case. I could draw the program to an end if the value of e is equal to 0. Alright? If the value of e is equal to 0, which value should be returned? The value of 1 should be returned. Or you can have another case. The first is, if the value of e is equal to 0, exponent, the value of 1 should be returned. However, if the value of e is equal to 1, again you can have another base case. And that is going to be, if the value of e is equal to 1, again, can I say like, the value of b could be returned? if there is a value of 2 which is raised to 1, which means, I could draw the program to an end. I could return the value of b. Say 3 raised to 1 will be 3 itself, 4 raised to 1 will be the 4 itself. So I can, if the value of exponent is 1, again, I can return the value of b and then draw the program to a close. So there are 2 ways to have the base case for this kind of program, alright? But we'll pick up the first one. Okay, so this is the function header. And then what comes next is, like I said, if the value of e is equal to 0, so this could be the base case. If the value of e is equal to 0, I return a value of 1. Okay? And that signals the end of the program. However, else, if the value of e is not equal to 0, then I should come up with the statement, all important statement of return, and then you will have b, alright, multiplied by the recursive call to the power function, and then you will always have b as it is, but I need to deduct the value of e by 1. Okay, b comma e minus 1. I guess that's the end of the program. It's very simple. So this will be the function definition for the power, and then we'll have the main statement, main part of the program. It's going to be something like, this is the main part of the program. Let's have the value of x is equal to 2, and then we'll have the value of n as 3. So this denotes the base and this denotes the exponent, right? And then result is equal to, let's call the function of power, and then we'll send both the variables of x and n. So this should be fairly simple. Let's not do this again. It will consume a lot of time, and I assume that you must have understood the drawings to a great length. Okay, so and then finally I'll have to print the value of result. Alright, so you have the function call, the value of x is 2, the value of n is 3. 2 will be received by b, 2 will be received by b, and then you will have the value of e as 3. Alright, so the value of e is 3, the condition becomes false, and then the return statement will be executed. So this will give us the result of the value of b being 2 into, again you have recursive call, the value of b will still be 2, and the value of e being 3 will now change to 2. Okay, so the result of the return statement of the first function call will be 2 into power 2 comma 2. Okay, so again you have a function call here. This will invoke the function itself all over again. So 2 will replace the value of b, and 2 will replace the value of e as well. Again, check the value of e, the condition is false. It then executes this return. Now this time you have this earlier 2 which will be stored as it is. So this, as a result of this, what happens is this as a whole will be executed again. This 2 is the earlier 2 of the first function call. Don't get confused. So this time, since this statement as a whole is being executed, you will again have the value of b as 2 into power of 2 into power of the value of b is still 2. E minus 1 is 1. E minus 1 is 1. Okay? Now I'm running short of the space. So at the end of the second recursive call, the result of the return statement will be 2 into power of 2 comma 1. So again, 2 will be received as 2 by B. However, the value of E will change from 2 to 1. Okay, so again the condition is false. The value of E being 1, it's not equal to 0. This statement will be skipped, and again this return statement will be executed. So this time, this 2 belongs to the 2 of the first function call. This 2 belongs to the 2 of the second function call. Now this time, fresh statement of return will be executed again. So this time it will be 2 into power of, you have power of, the value of B is 2, the value of E being 1, it will now change to 0. Alright? It will now change to 0. So this will be the final function call. So again, this will make a call to the function itself. Okay? 2 will be received as 2 in B. 0 will be the new value of E. I hope you have understood so far. So this time the condition becomes true. The value of E being 0, 0 is equal to 0. Return 1. Return 1. This 1 will now replace the function call via which the function definition has been executed. Which is that call that have resulted into the execution of this call, this function definition? It's this. Okay? So the 1 will be like an answer, to the call, to the last call. So 1 will now replace, this function call as 1. And then it will keep returning, the 1 will be returned, in the final call, as a result of which, 1 will be multiplied with 2, and then 3 as a value will be returned back to this. Okay, 2 times 2 times 2 will be 4, 4 times 2 will be 8. So the value will keep on getting returned from the individual frame, of the stack. So this is, how you should write a program with regard to calculation of a number or a base raised to another number. So regardless of whatever numbers you substitute for B and E, you will get the correct answer always. Okay? So, this is the fourth program. And then, like I said, sometimes, there could be infinite recursion, which means the recursive program is senseless or meaningless. So there could be 2 situations which could give rise to infinite recursive call. At times, you could be posed question during the examination. What are the possible situations which could give rise to the infinite recursive call? At times, if the user is allowed to enter, the value of n as negative. Okay? If the user is allowed to enter the value of -1, this -1 will be assigned to E. So as a result of which, this condition will never ever be true. I hope you're getting me. Let's say by chance, if somebody enters -1, you do have an exponent value as -1, but just in case, if you decide to set -1 will be the value of E. So in this particular situation, this condition will always be false. It will be here, and -1 will be -1 plus -1 is -2, -2 plus -1 is -3, -3 plus -1 is -4. This will go on, and this condition will never ever be true. So this particular situation is actually called as base case unreachable. Base case is never ever reached. So the first situation is if the base case is never ever reached, if the base case is unreachable, it could give rise to infinite recursive call, which will make the recursive program absolutely meaningless or senseless. Or at times, there could be a missing case of base case, which is so important in recursive program. So in order to prevent infinite recursive call, the first situation is the base case should be present as a part of your program. And the second important condition is not only should it be made available, but it should also be reached. Okay, otherwise if it's not reached, the program will go on and on. And then what happens is the program will keep eating up the spaces of the RAM. And then it could cause hindrance, or it could harm the working of other well-behaving programs. Say you have a downloading process going on, okay? So if this is not controlled, it will keep eating up the spaces, which will for sure hamper the other live or the active programs which are going on, which are live and kicking without any problem. But Python takes care of this. There is a limit called maximum recursion depth. It's a situation, it's a limit imposed by the Python. So once that particular depth is reached, the Python will report a runtime error. Okay, runtime error. The name of the error is maximum recursion depth. So it's supposed to be a value which will be flashed up on the screen, which means the program has crashed. So the operating system will cause the program to crash. It's better to destroy the program so that it will not result into destruction of other behaving programs. So this is how the Python will actually take care of the situation. So as a matter of home assignment, you could even try this. Compute, or I'll write it somewhere else. Say this could be a nice home task. Compute sum of squares, okay, of values from 1 to n. Okay, so you have a food for thought. You could actually try this. It's a part of the textbook questions. So again, it's just a matter of little twist in your thought process. You should be able to write the program, for this particular question. Compute sum of squares of values starting from 1 to n. So I would like to, before I call end to today's video lesson, let's do a quick recap of the topics that we have done. The first thing is you need to understand the very definition of recursion. The calling the function itself over and over again, and then immediately what should strike next is there are two important cases. The first one is you should have the recursive situation, and then you should also have the base case. Recursive case means there should be a situation where the function is calling the same function, the function itself over and over again. That's what we mean by recursive case. And then what is even more important is the base case. Base case is a situation where the program will come to an end. And then when you try to understand these programs, if not for the drawing of the frame and the drawing of the stack, it's literally impossible for you to understand the program. You need to do a lot of imagination. Okay, so at some point your imagination will come crashing. So it's so important that for a couple of the programs, at least if you could come up with a drawing in the form of stack and the frames, and then how the frame disappears of the stack one by one. So if you manage to grasp a clear picture of how the computer handles the function invocation, especially in terms of the recursive program, you will feel at absolute ease in understanding the remaining programs. Okay, so with this I would like to draw an end to today's video lesson, and then the next session will be the continuation of today's lesson. Until then, take care.